On October 23rd, while driving through Zhuhai District, Shanghai, a Li Auto Mega electric MPV suddenly burst into flames. Witnesses said there was no collision, yet the fire spread rapidly from beneath the vehicle, right where the CATL lithium battery pack was installed. Incidents like this remind us of one uncomfortable truth: lithium batteries still burn, no matter how advanced the EV looks. But what if Tesla is already preparing two battery technologies that don't burn, aluminum-ion and sodium-ion, both scheduled to appear in 2026? Clean, cheap, non-flammable, recyclable, and built to end the lithium era entirely. So let me ask you, if your daily commute suddenly became fireproof, would you trust EVs more? If your maintenance bill dropped by half, would you consider switching? And if Tesla really nails both battery projects, which chemistry do you think will dominate your garage? That's exactly what we're digging into today. Comparing both technologies, revisiting previous test data from the lab and the field, and highlighting key details you might have missed along the way. Before we start, make sure to subscribe and hit the notification bell so AutoGearshift can reach 17,171 subscribers. Help us hit that oddly satisfying number and unlock the next wave of deep dive EV tech content. This video brings together everything we've covered so far about these two next-gen batteries. Some parts may feel familiar, but I guarantee there's new critical information you haven't heard yet. So sit back and enjoy. This one ties the whole picture together. What's wrong with lithium-ion batteries today? For more than 10 years, lithium-ion batteries have powered Tesla's rise, from the early Model S to the upcoming Model 2. But behind their success lies a growing list of problems that can no longer be ignored. Let's start with how lithium is mined. To extract just 1 ton of lithium, companies need over 2 million liters of water, about 530,000 gallons, roughly what 10 average families use in a full year. Most of this mining happens in South America's Lithium Triangle, stretching across Chile, Bolivia, and Argentina, one of the driest regions on Earth. Farmers there say groundwater levels have dropped by up to 50% in some areas, and soil salinity is rising, making crops like corn and potatoes harder to grow. Every new battery factory that opens means more pressure on already limited water resources. Then comes the problem of recycling. Despite all the talk about green energy, only about 5% of the world's lithium batteries are fully recycled. The rest, nearly 95%, end up buried in landfills or incinerated, because separating materials like lithium, cobalt, and nickel costs more than mining new ones. A typical EV battery can weigh 400 to 600 kilograms, 880 to 1,300 pounds. And when it's dumped, those heavy metals don't just disappear. They can leak into soil and groundwater for decades. Safety is another concern. Lithium-ion batteries store massive amounts of energy in a small space. When a single cell fails or overheats, temperatures can reach 400 to 500 degrees Celsius, 750 to 930 degrees Fahrenheit, within seconds, hot enough to melt aluminum and ignite surrounding materials. That's why EV fires often spread fast and are extremely difficult to put out. Firefighters in several countries now use special immersion containers, essentially giant water tanks, to submerge burning EVs for hours just to cool them down. And then there's the supply chain. More than 70% of lithium and nearly 60% of cobalt, both key materials in Tesla's current batteries, come from China, Chile, and the Democratic Republic of Congo. These are politically sensitive regions where production is vulnerable to strikes, export bans, or environmental restrictions. When lithium demand exploded between 2020 and 2022, prices rose 5-fold, pushing up EV costs worldwide and forcing many automakers to delay affordable models. Lithium-ion batteries have taken us far. They made electric vehicles possible. But their water footprint, fire risk, recycling limits, and supply chain dependence show that this technology can't sustain the next generation of mass-market EVs. For Tesla, the future has to be cleaner, safer, and less fragile. And that's exactly where aluminum-ion comes in next. So now let me ask you this. If you had to choose the battery for your next electric car, comment lithium or aluminum to let us know. Let's see which side is the final winner. And don't forget to share why in the comments below. I'd love to hear your thoughts and real-world opinions. Why is aluminum-ion considered the green battery? If the world wants electric cars that are truly clean, not just at the tailpipe, then the biggest change has to start inside the battery. That's where aluminum-ion steps in, and it's earning the nickname green battery for good reason. First, aluminum is everywhere. It's the second most abundant metal on Earth, making up about 8% of the planet's crust, right after iron. You can find it in rocks, clay, and even in recycled scrap metal. Unlike lithium, which is mined mostly in South America and Australia, nearly every country can produce or recycle aluminum locally. That means no single nation controls the supply chain, and the risk of price spikes or shortages, like we saw with lithium, becomes almost zero. Second, aluminum is one of the most recyclable materials ever created. It can be recycled 100% without losing quality, and it can be reused an unlimited number of times. The best part? Recycling aluminum takes only about 5% of the energy needed to make new aluminum from raw ore. In practical terms, if the battery industry switched from lithium to aluminum, global energy use for making batteries could drop by over 90%. That's not just a technical improvement. It could save billions of kilowatt-hours of electricity every year and cut millions of tons of carbon dioxide emissions from metal refining and transport. Third, aluminum-ion batteries are free of cobalt and nickel, two of the most controversial metals in modern batteries. Mining cobalt often takes place in unsafe conditions, especially in the Democratic Republic of Congo, where reports show tens of thousands of workers, including children, exposed to toxic dust and accidents. Nickel mining also creates acidic waste that contaminates rivers and farmland. By removing both, aluminum-ion avoids one of the biggest environmental and ethical problems in the EV industry. When it comes to safety, aluminum-ion chemistry is on another level. Instead of using flammable organic solvents like in lithium-ion cells, aluminum batteries use solid electrolytes or stable ionic liquids, substances that don't ignite even when heated. Tests show that when an aluminum-ion cell is punctured or crushed, it only gets warm, typically under 100 degrees Celsius, 212 degrees Fahrenheit, and does not catch fire. In comparison, a damaged lithium-ion cell can quickly hit 400 to 500 degrees Celsius, 750 to 930 degrees Fahrenheit, and burst into flames within seconds. Another advantage: aluminum-ion batteries don't release hydrogen fluoride, a poisonous gas that forms when lithium-ion batteries burn. All of this adds up to one clear conclusion. Aluminum-ion batteries are not just another new technology. They are a cleaner, safer, and far more sustainable option. With abundant raw materials, infinite recyclability, and almost zero fire risk, this chemistry could allow Tesla, and the entire EV industry, to finally move beyond lithium towards a battery future that's better for both drivers and the planet. What happens if Tesla adopts aluminum-ion? If Tesla truly brings aluminum-ion batteries into its production line, it could trigger the biggest shift in the electric vehicle market since the birth of the Model 3. The most immediate effect would be price. Right now, the battery pack alone accounts for up to 40% of an EV's total cost. For example, the average lithium-ion battery costs about $110 to $130 per kilowatt-hour, depending on chemistry and source. Aluminum-ion batteries, because they use cheaper raw materials and simpler recycling processes, could lower that cost by roughly 25%. That means the upcoming Tesla Model 2, expected to use a 40 kilowatt-hour pack, might see its battery cost drop from about $5,000 to closer to $3,700. With that savings, Tesla could realistically sell the Model 2 for around $13,500, becoming the first automaker in the world to launch a fully electric car under $15,000. For comparison, even the cheapest BYD Dolphin Mini in China still costs around $16,000 to $17,000, and most Western EVs are double that. If Tesla manages to break this barrier, it could open the EV market to millions of new buyers worldwide, especially those who previously couldn't afford an electric car. The second major impact is waste reduction. A single electric vehicle typically carries a battery pack weighing between 400 and 600 kilograms, 880 to 1,320 pounds. As global EV sales surpass 15 million units per year, that's roughly 7 to 9 million tons of new batteries entering circulation annually. Today, less than 5% of lithium-based batteries are recycled properly, meaning most of that material becomes landfill or industrial waste. But if Tesla switches to aluminum-ion, which can be recycled infinitely without losing quality, those same tons of used batteries could be melted, purified, and returned directly to gigafactory production lines. In theory, this could eliminate millions of tons of waste every year and create the world's first zero-waste battery manufacturing loop. This also ties into Tesla's long-term cost strategy. Recycling aluminum uses only 5% of the energy required to refine new aluminum from ore, which means Tesla could drastically cut both energy bills and carbon emissions across its factories. Instead of depending on mines in Chile, Congo, or Indonesia, where labor and environmental issues often raise controversy, Tesla could source most of its aluminum domestically or from recycled scrap metal. That's not just good for the planet, it's good business. Localized supply means fewer shipping costs, fewer political risks, and far more stable production planning. And if Tesla proves this system works, the ripple effect across the industry would be unavoidable. Competitors like BYD, Ford, and Rivian would have no choice but to follow, because consumers and investors alike will demand cleaner, cheaper, and safer batteries. Within just a few years, possibly by 2026 or 2027, the global EV battery market could start shifting away from lithium toward aluminum-based solutions. So if Elon Musk succeeds in scaling aluminum-ion technology, it won't just lower EV prices. It could redefine the entire meaning of clean energy. From reducing costs and pollution to cutting the world's battery waste to nearly zero, Tesla's move could signal the beginning of the end for lithium's 30-year reign. How about you? Would you trust an aluminum-ion Tesla if it means zero fire risk and lower prices? Or do you believe lithium still has room to improve before we move on? Let me know your thoughts in the comments below. I read every one of them.
For more than a century, the limits of the car have been the same: distance, time, and cost. Now Tesla says those limits are about to disappear. The company's newest creation, the 2026 Model 2, promises a range of 1,759 miles on a single charge, a full recharge in about 5 minutes, and a $5,678 retrofit that could give existing Teslas the same power. It's called the aluminum-ion battery, a technology once dismissed as impossible. Now ready for production, Elon Musk calls it a gigantic revolution in energy. But for many drivers, it's something simpler: freedom. Fewer stops, lower bills, and a car that could outlast its own design cycle. 1. How Tesla plans to redefine the EV battery game. Aluminum-ion batteries are not new. Scientists have been experimenting with them for years, drawn by aluminum's abundance, low cost, and superior safety profile compared to lithium. But for most of that time, the dream ran into 3 walls: stability, energy density, and integration. The chemistry struggled to hold charge efficiently, degraded quickly, and couldn't easily fit into the existing electric vehicle architecture. Tesla's approach changes that equation, or at least that's the claim. Instead of developing a far future concept car, Musk's engineering team reportedly designed a cross-platform battery system that could slide into existing Tesla architectures. They call it CPMI, the Cross-Platform Module Interface. Think of it like a universal heart transplant. Rather than redesign the entire car, Tesla can replace the battery organ with minimal re-engineering. This philosophy aligns with what Tesla has quietly been building toward since 2021, modularity. In Fremont, Austin, and Shanghai, production lines have been standardized down to the millimeter, from cooling plates to chassis mounting points. The message is clear. Tesla doesn't just want to build new cars. It wants to upgrade old ones from the inside out. The rumored aluminum-ion module measures about 70 inches long, 55 inches wide, and weighs roughly 1,250 pounds. That's not an arbitrary figure. It matches the form factor of Tesla's current skateboard-style battery packs. If accurate, this would mean Tesla could potentially retrofit aluminum-ion packs into cars produced since 2021 without changing the core vehicle structure. And that's revolutionary, not just technically, but economically. You don't need a new car, you just need a new heart. Seeing this far, you are probably skeptical about the information we're sharing. The truth is, Tesla has not publicly confirmed any aluminum-ion mass production line, nor has it presented the chemistry at any official event. Still, whispers from the supply chain and R&D circles suggest that Tesla has been experimenting with aluminum-based prototypes at a pilot scale. The company's investment in modular design adds credibility to the concept. Meanwhile, the global aluminum-ion battery market, though still in its infancy, is projected to expand rapidly. According to Future Market Insights, the market was valued at approximately $5.6 billion in 2025, with growth expected to reach $9.5 billion by 2035, a modest compound annual growth rate of 5.5%. However, Market Research Future paints a far more aggressive picture. The market could climb from $2.0 billion in 2024 to $25.2 billion by 2035, reflecting a compound annual growth rate of 25.9%. These differing forecasts reveal a fundamental truth. No one really knows how quickly aluminum-ion technology will mature. What is clear, however, is that the demand for next-generation batteries is real, driven by soaring EV sales, tightening resource supply chains, and the quest for safer, more affordable alternatives to lithium-ion. But how exactly does Tesla plan to make this seamless battery upgrade a reality for millions of drivers? And, more importantly, what does this mean for the future of your current Tesla? 2. The retrofit revolution. Upgrade instead of replace. If Tesla's vision comes to life, it could reshape the auto industry. For decades, automakers have thrived on planned obsolescence, forcing consumers to buy new models for new technology. Tesla is turning that logic upside down. With this new battery, a 2022 Model 3 could soon outperform a competitor's brand new EV. That's because this new battery isn't just a component, it's a software-defined energy system. Aluminum-ion cells operate at an average 20 volts per cell, compared to around 3.8 volts for lithium-ion. That high voltage would traditionally fry an EV's electronics in seconds. Tesla solved this with a multi-chemistry management system that automatically adjusts inverter behavior and power distribution in real time. This digital system reads voltage and temperature data from each module and rewrites the inverter commands, all via software updates over the air. In other words, your car could learn to speak a new chemical language overnight. Tesla's engineers have gone even further with cooling technology. Using microchannels of coolant to prevent heat buildup, excess heat is routed to a metal plate acting as a heatsink, all sealed in a CPMI sled, requiring no modifications to the vehicle's existing cooling system. And here comes the game changer. Tesla's claimed retrofit package, a 60 kilowatt-hour aluminum-ion module delivering over 1,000 miles of real-world range is priced at about $5,678 installed. That's less than a flagship smartphone. For that price, a Model Y owner can triple their range and have charging time, all without new taxes, registration fees, or insurance resets. For traditional automakers, this seems suicidal. But for Tesla, it's a different strategy, one that's already paying off. Musk isn't trying to sell more cars. Instead, he's building a living ecosystem where profits no longer come solely from hardware, but from services, upgrades, AI features, and energy integration. Every retrofit helps extend the customer relationship without producing a single new chassis. Now let's have a short discussion. If you believe that aluminum batteries will appear with Tesla Model 2, leave a Y in the comments section. If you have a different opinion, leave an N and share your reasons. Now continue to follow the last part of today's episode to answer the question, how could your Tesla not just power your drive, but also help power the grid? 3. The energy shift. Powering the grid, not straining it. A 1,579-mile battery that recharges in just 5 minutes sounds almost too good to be true. The obvious concern is, can the US grid handle that load? Tesla's answer is energy intelligence. Each Generation 54 supercharger will be paired with a Megapack, a massive stationary battery with up to 3.9 megawatt hours of capacity. These units store electricity at night during off-peak hours and release it during the day, turning every charging station into a mini power plant. When a Tesla driver plugs in for a 5-minute ultracharge, they're not drawing live energy from the national grid. They're tapping stored energy generated earlier, helping stabilize the grid rather than strain it. Tesla's Texas Gigafactory alone can produce over 10,000 megapacks per year, enough to power thousands of next-generation stations across North America. At home, about 80% of EV charging still happens overnight, between 2 a.m. and 5 a.m., when grid demand and energy costs are at their lowest. Even with aluminum ion's extreme fast charging potential, this pattern remains efficient. The new battery simply adds flexibility, turbo mode on demand. But Tesla's ambitions don't stop there. With such high energy density, aluminum ion Teslas could serve as mobile batteries, returning energy to the grid when needed, a concept known as vehicle-to-grid early pilot programs in US neighborhoods are already showing promising results. In that future, your Tesla doesn't just consume power, it stabilizes it. Your car becomes part of the national energy infrastructure, helping to balance grid supply and demand. Tesla's aluminum-ion strategy isn't just a product release, it's a redefinition of what an automobile can be. A machine that upgrades itself, a battery that outlasts the car around it, a network that powers both the driver and the grid.
So our cell production is going quite well, and I think we're currently sort of the lowest cost per kilowatt hour.
Yeah.
We have the lowest cost per kilowatt hour, all things considered. So the Tesla cell is the most competitive cell.
Those words from Elon Musk weren't random. They were the quiet unveiling of Tesla's next big weapon, the sodium-ion battery, or what some call the salt battery. While most people overlooked it, this was the moment Musk signaled the beginning of the end for lithium. And with Tesla's Battery Day, these clues are no longer subtle, they're impossible to ignore. So why sodium-ion? And why now? And how will this shockwave ripple across the EV world in 2026, rewriting everything we thought was good enough? 1. Why is Tesla developing sodium-ion batteries to eliminate lithium-ion batteries in 2026? Over the past 3 years, the price of lithium carbonate has exploded by over 300%, jumping from $13,000 per ton in 2021 to more than $70,000 per ton by late 2024. That single data point alone tells the truth. Lithium is no longer scalable. And this crisis goes far beyond price. More than 75% of global lithium refining is controlled by China, and 99% of lithium iron phosphate production comes from the same source. Meanwhile, lithium extraction consumes over 500,000 gallons of water per ton, devastating local environments in South America and Australia. And let's not forget the cold financial reality. Lithium-ion batteries degrade after just 1,500 to 5,000 full cycles, costing 10,000 to 20,000 United States dollars to replace on a Model 3. That's why Elon Musk dropped the bombshell on Tesla's 2024 Q4 earnings call.
Well, right now the constraint we're trying to solve is battery production as opposed to demand. So just before this call was we've got to figure out how to increase total gigawatt hours of battery production this year one way or another. That's the constraint on our output.
Gigafactories in Texas and Berlin are operating at only 60% capacity, not because of poor design, but because they can't get enough lithium. And here's the terrifying truth. To scale lithium production to meet future goals, Tesla would need to build over 100 new gigafactories, each costing billions and taking years. That was the moment the sodium-ion battery entered the market. Musk's obsession with increasing total gigawatt hours of battery production points directly to the sodium ion's unlimited scalability. While lithium deposits max out at 100 million tons globally, sodium is the sixth most abundant element on Earth, with billions of tons available in soda ash and seawater. Tesla can build sodium-ion factories faster and produce batteries at an unprecedented scale, potentially 158 gigawatt-hours globally by 2026, with Tesla targeting 20 to 30 gigawatt-hours for its electric vehicles. The financial impact is staggering. Sodium-ion could slash battery costs by $5,000 to $10,000 per vehicle, saving Tesla $100 billion annually at 20 million cars. These batteries use non-toxic, non-flammable materials, completely eliminating Tesla's dependence on blood cobalt and conflict nickel. If you believe this, type sodium-ion in the comments. 2. How incredibly do mind-blowing capabilities make sodium-ion a game-changer? Deep inside these revolutionary cells are microscopic nanocells that perform what can only be described as digital magic. When a sodium-ion cell degrades from normal use, neighboring cells instantly release repair compounds that literally rebuild the electrode structure in real time. This self-healing chemistry is so advanced that in early stress tests, Tesla's sodium batteries maintained 95% capacity after 12,000 deep cycles. But Tesla's real breakthrough lies in their hyper-fast charging capabilities that make current superchargers look like dial-up internet. Sodium ions move through Tesla's revolutionary quantum channels at subatomic speeds, achieving the impossible: 0 to 100% charge in just 4 minutes and 32 seconds during internal testing. About the physics-defying aspect, the battery actually stays cooler during ultra-fast charging than during slow charging, completely inverting everything we thought we knew about battery thermodynamics. Thermal immunity represents Tesla's most explosive advantage. Tesla's sodium-ion battery can survive direct flame contact for over 90 seconds without combustion, while lithium packs ignite in less than 15 seconds under identical thermal abuse. The longevity numbers are equally mind-bending. Sodium-ion's advanced chemistry supports 20,000 charge cycles, equivalent to 2 million miles or 50 years of continuous driving. Tesla's sodium-ion technology is already pushing 250 watt-hours per kilogram with sodium iron phosphate cathodes, directly rivaling lithium-ion's 250 to 300 watt-hours per kilogram range, and ready for mass production immediately. The production economics are equally devastating to competitors. Aluminum ions complex graphene cathodes cost $150 to $200 per kilowatt hour to manufacture and require exotic materials that don't exist on a scale. In contrast, Tesla's sodium ion is built from table salt and iron, costing just $80 to $90 per kilowatt hour. This amount is cheap enough to power a $15,000 Tesla that makes electric vehicles accessible to every human on Earth. 3. How will Tesla's sodium-ion battery ignite a global EV revolution? Tesla Model 2 represents Tesla's most explosive weapon in this revolution. Internal testing reveals this compact powerhouse can deliver a staggering 435-mile range, which is over 50% more than any gasoline car in its class. But here's the nuclear bomb. Tesla's sodium-ion technology could make this vehicle cheaper than a Honda Civic, slashing total ownership costs by $60,000 over 15 years due to zero fuel costs and zero battery replacements. Tesla's Model 3 and Model Y are getting equally devastating upgrades. Sodium-ion technology will push their ranges to 550 to 650 miles by 2026, permanently obliterating range anxiety from human consciousness. With charging times dropping to just 8 minutes for 0 to 80% capacity, Tesla owners will spend less time at superchargers than gasoline drivers spend at gas pumps. The pricing earthquake is equally brutal. Model 3 could drop to $29,999 and Model Y to $34,999, undercutting every competitor by margins that make competition mathematically impossible. Commercial vehicle domination is even more catastrophic for traditional manufacturers. Sodium-ion's 20,000 cycle lifespan enables a Cybertruck with 700-mile range that operates for 50 years without degradation, while the Tesla Semi can run 24 hours per day for 2 million miles without a single battery swap. This breakthrough could slash global logistics costs by 40%, making Tesla the indispensable backbone of worldwide transportation infrastructure. Every delivery truck, every long-haul semi, every commercial fleet will be forced to convert or face economic extinction. Tesla's energy storage revolution extends far beyond vehicles. Sodium-ion megapacks could crash grid storage costs to just $50 per kilowatt hour, powering entire cities with renewable energy for literal pennies. A single megapack could store enough energy to run 10,000 homes for an entire day, cutting electricity bills by 30% nationwide. Tesla isn't just building cars. They're constructing the energy infrastructure that powers human civilization. Every consumer pain point gets annihilated simultaneously. Range anxiety becomes a historical curiosity when your Tesla delivers 550 to 700 miles per charge, eliminating the need for mid-trip charging even on 2,000-mile cross-country road trips. The financial impact is staggering: $60,000 to $100,000 in lifetime savings per vehicle due to lower battery costs, zero replacements, and zero fuel expenses. Next, million-mile battery durability means Tesla resale values could be 40% higher than any lithium-ion competitor, turning your vehicle purchase into a wealth-building investment rather than a depreciating asset. Sodium-ion makes every Tesla a legacy you pass down to future generations, not a disposable consumer product you replace every few years. While competitors desperately chase $100,000 luxury supercars for the wealthy elite, Tesla is building a $19,000 Model 2 that outshines them all in every meaningful metric.
Elon Musk is preparing to launch a battery no one in the auto industry thought possible: a sodium-ion pack with zero lithium, zero cobalt, and zero nickel. While China is already mass-producing its own sodium-ion cells, Tesla is betting on a completely different chemistry, one designed to cut costs, boost safety, and change the game. How can NFPP sodium-ion outperform today's lithium batteries? Tesla's bet centers on a chemistry called sodium iron phosphate pyrophosphate, or NFPP. Unlike conventional batteries, it contains no lithium, cobalt, nickel, manganese, or rare earth elements, eliminating the supply chain chokehold that keeps most automakers tied to China. Instead, it uses abundant materials: sodium derived from soda ash, iron, phosphorus from phosphate rock, carbon for the anode, and aluminum as the current collector. That shift alone is massive, because it means production could be scaled with resources readily available inside the United States. On a molecular level, NFPP is built for stability. The cathode's crystal structure is resistant to breakdown and does not release oxygen, which removes the root cause of thermal runaway. This is a battery that doesn't catch fire, doesn't explode, and can be drained to 0% without damage. Its discharge window runs from 4 volts down to 2, giving engineers more accurate state-of-charge readings than lithium-ion. It also keeps performing in brutal conditions, down to -40 degrees Celsius and up to 60 degrees, thanks to an electrolyte that allows sodium ions to move freely even at freezing temperatures without forming dangerous dendrites. The engineering advantages stack up quickly. NFPP cells don't need complex liquid cooling or HVAC systems. They can rely on passive thermal management, slashing parasitic energy losses by as much as 90% compared to lithium-ion. Their cycle life is remarkable: full 100% depth of discharge cycles with minimal degradation, making them ideal for both vehicles and grid storage. They can even be shipped at 0 state of charge, unlike lithium packs that must be held at around 30% and treated as hazardous cargo. With no moving parts, no need for fluid top-offs, and roughly 20% lower cost than the best lithium systems on today's market, NFPP offers a compelling case for mass deployment. The geopolitical angle is just as important. While current lithium, cobalt, nickel, and manganese supplies are dominated by global mining and refining controlled largely by China, where 60 to 70% of lithium, 70 to 80% of graphite, and 90% of manganese are processed, the sodium, iron, and phosphorus required for NFPP can be mined and refined domestically. Wyoming, for example, holds the world's largest reserves of soda ash, giving the U.S. a unique chance to localize production and break away from dependence on Chinese supply chains. Where does it fit in practice? NFPP is being positioned primarily for grid-scale energy storage, where safety, cost, and durability matter more than packing maximum range into a vehicle. But the chemistry's potential doesn't stop there. Its energy density falls short of nickel-manganese cobalt cells used in luxury EVs, but it matches lithium iron phosphate packs that already power mainstream cars. That makes it a candidate for affordable EVs, giving Tesla the building block it needs to hit the $17,000 Model 2 price point. In fact, the largest NFPP system in the US is already online, tied into Montana's Flathead Electric Cooperative, while China has pushed forward with a separate 100 megawatt-hour sodium-ion project in Shenzhen, using a different oxide-based formula. The company driving much of this NFPP work in the US is Peak Energy, a Colorado startup founded in 2023 by former Tesla and NRG engineers. It holds patents, has built demonstration units connected to the grid, but still lacks the manufacturing scale of Chinese giants. Its domestic rival, Natron Energy, is pursuing a different sodium-ion chemistry aimed at data centers. Overseas, CATL and BYD are pouring billions into sodium-ion development, focusing on PBA-based chemistries with mass production slated for 2025. The contrast is clear. China is racing to scale while Tesla and Peak Energy are trying to differentiate through chemistry. The long-term vision is that sodium-ion could finally deliver what Elon Musk has been promising for years: an EV that is good enough, with 200 to 250 miles of range, a safer battery, longer life, and a price tag that truly makes electric cars accessible. Whether NFPP becomes Tesla's ace in the hole or remains a niche solution will depend on how fast production can scale. But one thing is certain, the industry is watching closely, because this is no longer just theory, it's already being tested in the field. And here's where it stacks up against the competition. NMC cells dominate premium EVs because of their high energy density, giving 300 to 400 miles of range, but they're extremely expensive and tied to cobalt and nickel supply chains that are not only toxic to mine, but also highly volatile in price. Worse, they're prone to thermal runaway, which is why fire recalls keep making headlines. LFP packs, on the other hand, cut costs and improve safety, making them popular in mass-market EVs. But they still depend on lithium, and nearly 70% of global refining happens in China. That leaves automakers vulnerable to geopolitical bottlenecks and price swings. NFPP sodium-ion doesn't just sidestep those issues. It uses sodium, iron, and phosphate that can be sourced locally, reducing costs by roughly 20% versus the best lithium systems, while offering superior thermal stability and cycle life. The trade-off is lower energy density than NMC, meaning 200 to 250 miles of range instead of 350 plus, but for affordable EVs and grid-scale storage, that balance of cost, safety, and independence could be the real disruptor. Would you trust a battery that doesn't catch fire and lasts longer for your everyday car? If you agree, comment sodium-ion below. And share, what's your biggest concern about EV batteries today? Don't go anywhere because we have more to come. Why Tesla's NFPP could outlast CATL's sodium-ion rush. China's battery giants CATL and BYD are racing ahead, unveiling their second-generation sodium-ion cells under the Naxtra brand and preparing for mass production by late 2025. They've already shown off real-world scale with a 100 megawatt-hour project in Shenzhen, and their packs are undeniably cheap and safe compared to NCM. On the surface, it looks like an unstoppable advance. But here's the catch. The Chinese designs lean on oxide-based PBA chemistry, a shortcut that cuts cost today but sacrifices long-term stability, cycle life, and efficiency under stress. In other words, Naxtra might be good enough for entry-level EVs or grid storage, but it's not engineered for durability or precision performance. Meanwhile, Korean competitors, LG, Samsung, SK On, are struggling to adapt. Their sodium-ion roadmaps don't even target commercialization until 2030, and their global EV battery share has already collapsed from over 30% in 2021 to just 16.4% in 2025, while China has soared to nearly 78% dominance. The battlefield is clear: cheap, fast-to-market Chinese packs versus lagging Korean incumbents. This is where Tesla's Model 2 flips the script. Instead of chasing volume like KTL or waiting like Korea, Tesla is building around NFPP chemistry, a sodium iron phosphate pyrophosphate system designed for unmatched safety, durability, and US-sourced independence. NFPP cathodes remain stable under extreme stress, don't release oxygen, and can safely discharge to 0% without damage, something oxide-based rivals can't match. Add in its ability to function from -40 degrees Celsius to 60 degrees Celsius, with no dendrite formation and no thermal runaway, and Tesla's sodium-ion instantly becomes the most abuse-tolerant chemistry ever aimed at mass-market EVs. And the payoff? The Model 2 could hit the road with a 200 to 250-mile range at under $17,000, with a pack that costs about 20% less than today's best lithium systems, all while being built from materials mined and refined in America. No dependency on Chinese lithium, no waiting for Korean labs, no shortcuts on safety. CATL may pump out sodium-ion cells first, but Tesla is preparing a battery platform that could outlast, out-safety, and out-economize every rival, making the Model 2 not just another budget EV, but the only affordable EV that doesn't compromise on independence or performance. While CATL and BYD are racing to flood the market with cheap sodium-ion packs, and Korea is still years behind. Tesla is taking the harder but smarter path. By betting on NFPP, Musk isn't just chasing numbers. He's building a battery that's safer, more durable, and made with materials that can be sourced right here in America. And that's exactly what makes the Model 2 different. Not just another budget EV, but potentially the first truly independent, affordable electric car for the global market. Do you think Tesla's NFPP chemistry is the real breakthrough to beat China's dominance? And most importantly, if the Model 2 does launch with this battery, would it finally convince you to switch to an EV?
We build our own seats, we build our own motors, we build our own battery packs.
With this statement, Tesla is killing lithium, the very metal that made its fortune.
I think it'll be 10 times bigger than the next biggest product ever made.
But why would Elon Musk replace the world's most successful battery with salt and aluminum? Sounds crazy, right? But those two elements might just be the secret to the next energy revolution. Aluminum-ion and sodium-ion technologies could mark the biggest leap in EV batteries since the first Model 2 rolled off the line. They promise ultra-fast charging, as quick as 60 seconds, cooler operation than any lithium cell, and prices less than half of today's packs. We'll uncover how Tesla's 2026 aluminum-ion and sodium-ion batteries could slash costs by 70%, redefine safety forever, and end lithium's 30-year reign once and for all. If you're tired of marketing talk and want the truth about the tech that really drives change, hit subscribe and ring the bell. Let's push autogearshift past 12,557 subscribers and keep real car talk alive for people who care about machines that work, not just promise. Why aluminum and sodium could beat lithium and make EV batteries super cheap. Most of us remember when a gallon of gas cost under $2, right? Now imagine the same kind of inflation, but for the fuel that powers electric cars. That's what happened with lithium. Back in 2022, lithium carbonate shot up to $80,000 a ton, about 10 times its pre-pandemic cost. Even now, in 2025, it hasn't really come back down. It's floating between $14,000 and $17,000. This quiet number is the reason EVs still cost more than most people want to pay. Because when lithium stays high, battery packs can't drop below roughly $100 to $130 per kilowatt hour. And that means a battery, just one battery, still eats up nearly a third of what a car costs to make. But here's the curveball. Tesla and other labs are testing two elements most of us have sitting in our kitchens: aluminum and sodium. On paper, they sound boring, but their numbers break the math that's been holding electric vehicles hostage. Aluminum trades at about $2,000 to $2,500 per ton, roughly 7 times cheaper than lithium. Sodium, pulled straight from salt or seawater, costs under $300. If Tesla can perfect a mix of aluminum-ion and sodium-ion chemistry, the entire pack could drop below $30 per kilowatt-hour. That's the same target Elon Musk threw out back on Battery Day in 2020, when most people thought it was a stretch. Here's what that actually means. Take a standard EV where the battery costs $8,000. Swap in aluminum or sodium, and that number could fall to $2,000, or even lower. Suddenly, the $25,000 Model 2 isn't some PR dream. It's an economically sound product, with room left for profit. MIT's Energy Initiative ran the numbers and found that sodium-ion alone could reduce global EV battery material costs by as much as 40%. That's not just cheaper. It's a change in the ground beneath the auto industry's feet. You can't compete with a chemistry that's both local and infinite. But here's where it gets even more disruptive. The economics scale like nothing we've seen before. Unlike lithium, which comes mostly from a handful of countries, Australia, Chile, and China, both aluminum and sodium are everywhere. Aluminum is the most abundant metal in Earth's crust. Sodium? It's literally in seawater. That means no more supply bottlenecks, no geopolitical choke points, and no rare earth dependency driving prices up. Refining lithium is expensive, slow, and environmentally harsh. You need evaporation ponds, acid leaching, and months of processing before it's battery grade. Aluminum and sodium skip most of that. Aluminum smelting is already an industrial backbone. Sodium can be extracted with simple chemical separation. Less refining means less cost per ton, and fewer middlemen taking their cut. Analysts at Bloomberg NEF estimate that if sodium-ion or aluminum-ion production scales just to 10% of global EV demand, raw material costs alone could fall by another 20 to 25% within 5 years. Combine that with localized US or European production, no overseas shipping, no tariffs, and the pack price could realistically fall to $25 per kilowatt hour. At that point, batteries stop being the most expensive part of an EV. They become the cheapest. And when energy storage becomes cheap and endless, the ripple effect doesn't stop with cars. It changes everything from grid storage to home power systems. Yes or no? Is this the battery breakthrough we've all been waiting for? Drop your thoughts below, because what comes next might prove it really is. How Tesla decides which battery is truly safe, aluminum or sodium. Elon Musk once said,
At Tesla, we're absolutely hardcore about safety.
And in the battery world, that isn't just a slogan, it's an engineering religion. As Tesla weighs two next-generation chemistries, aluminum-ion and sodium-ion, the question isn't only which one is cheaper. It's which one can survive a lifetime of heat, cold, impact, and neglect without turning into a fire hazard. Lithium-ion, for all its brilliance, has a nervous temperament. It's powerful but unstable, like a racehorse that kicks when startled. Both aluminum and sodium promise calmer behavior, but in very different ways. Sodium-ion batteries are chemically modest. Sodium doesn't form the sharp metallic dendrites that plague lithium, those microscopic needles that pierce separators and trigger short circuits. In 2024, TATL ran a brutal series of tests, nail punctures, open flames, and even direct crushing, and the sodium cells didn't ignite once. A lithium pack under the same abuse burns within seconds. Sodium's chemistry is simply less volatile. Its ions carry charge without the same eagerness to react with moisture or oxygen. Add to that its ability to keep 90 to 95% of its capacity even at minus 20 degrees Celsius, and you have a battery that feels like it was designed for Canada rather than California. The trade-off? Sodium ions are bulkier and heavier than lithium, which means slower diffusion and shorter life, roughly 2,000 to 4,000 charge cycles compared to lithium's 5,000 plus. Overcharging can also swell electrodes, which Tesla would need to manage with precision software and cell balancing. Still, in the grand safety hierarchy, sodium ion sits comfortably near the top. Stable, tolerant, predictable. Aluminum ion is another creature entirely. It doesn't behave like a softer lithium cousin. It behaves like an armored soldier. The cells rely on graphene or carbon-based cathodes, materials that can endure extraordinary current and heat. University of Queensland tests in 2023 showed aluminum-ion prototypes surviving 10,000 full cycles with zero recorded thermal runaway. Even under temperatures exceeding 120 degrees Celsius, they held structural integrity. Their electrolyte is a non-flammable ionic liquid, which means even if you puncture the cell or drive a nail through it, there's no combustion, just a dull hiss. The paradox, however, is that aluminum's strength hides a fragility. It reacts aggressively with water. A single droplet inside an unsealed pack could trigger corrosion or gas buildup. So while sodium's danger lies in overcharging, aluminum's lies in imperfection. Tesla would need absolutely dry manufacturing rooms and perfect sealing tolerances, a margin that only automated gigafactories can achieve. In return, the reward is enormous. Heat resistance, ultra-fast charging, and an operational lifespan approaching the mechanical durability of an engine block. So, which battery truly wins Tesla's safety race? If lithium-ion is a high-strung athlete, fast but temperamental, Then sodium-ion is the calm engineer and aluminum-ion the armored guardian. In raw safety terms, sodium-ion edges ahead in chemical stability. It shrugs off abuse, cold weather, and moisture without flaring up, making it ideal for mass-market models like the Tesla Model 2, especially in colder regions of North America and Europe. It's forgiving, predictable, and perfect for everyday commuters. Aluminum-ion, meanwhile, is the fortress. Its ionic liquid electrolyte and carbon-based architecture can survive heat, punctures, and crushing forces that would destroy any lithium pack. But it demands precision, airtight factories, dry environments, and flawless assembly. That makes it better suited for premium or performance EVs, where Tesla can control every manufacturing detail. So when Elon said lithium is outdated, what did you think? He's right or it's too soon? Comment to let us know your point. How Tesla plans to build the first non-lithium battery fleet by 2026. When Elon Musk calls something the next industrial revolution, he's talking about the Model 2. This isn't just another car. It's Tesla's first step toward a battery future that doesn't rely on lithium at all. Inside Giga Texas, Tesla is preparing the world's first aluminum-ion pilot line, built to power the Model 2 from day one. Early reports suggest a partnership with Redwood Materials, closing the loop by recovering aluminum and carbon directly from industrial scrap instead of mining fresh ore. Every cell produced could be partly recycled by design, a world first in EV manufacturing. Here's the rollout plan insiders are watching. By early 2026, Tesla aims to complete internal testing on the first aluminum-ion packs for prototype Model 2s. By mid-2026, these batteries could enter mass assembly, debuting alongside the $25,000 Model 2 itself. Meanwhile, sodium-ion packs are expected to serve colder markets and entry trims, where stability outweighs extreme range. Together, they form a dual chemistry strategy: aluminum for performance, sodium for everyday reliability. Do you want the near-instant charge and aerospace-grade stability of aluminum-ion, or the cool-running, cost-cutting resilience of sodium-ion? It's not about chemistry, it's about trade-offs, safety, speed, and what kind of future you're betting on. Tesla leaks aluminum-ion promises extreme speed, 60 times faster charging and triple the energy of lithium. Sodium-ion offers lower range but cheaper materials. But the question that lingers for many of us who keep our cars for decades isn't only about speed, it's about time. How long before the pack fades? What will it cost to replace? And what happens to all that material once it's done powering the car? In 2026, Elon Musk plans to answer those questions. Tesla's upcoming aluminum-ion and sodium-ion batteries aren't just tweaks to the existing formula. They're a philosophical split in how we think about durability, cost, and sustainability. So what's really hidden behind Musk's dual battery strategy? Let's deep into this video. How could a Tesla battery outlast the car itself? Elon Musk isn't just trying to make a better battery. He's trying to erase the idea that batteries die. The 2026 Tesla cell isn't designed to last longer. It's designed to outlast time as we measure it in cars. Let's start with the aluminum-ion cell, the stranger of the two. On paper, it looks like a paradox. A metal that corrodes easily and conducts heat too well somehow becomes the foundation for a cooler, faster, more stable battery. In early lab results, aluminum-ion cells recharge up to 60 times faster than lithium-ion. That's not an improvement. That's a category shift. A 25-minute supercharge could, in theory, shrink to under a minute. And because aluminum can hold 3 times the energy per unit weight, the same battery volume that now gives a 300-mile range could reach 900. The chemistry reads like science fiction, but the data has been quietly piling up since 2022 in research papers from Queensland and Stanford. Durability is where the story stops sounding like marketing and starts sounding like physics rewritten. Lab tests show over 2,000 full charge cycles before noticeable decay. roughly 1.5 to 2 million miles of driving. Not just endurance, but a collapse of the usual battery life cycle. The concept of replacement starts to lose meaning. The limiting factor may no longer be the battery, but the driver's lifespan. Then comes the sodium-ion cell, humbler, cheaper, but oddly resilient. It sacrifices about 10 to 20% of range compared to lithium, yet keeps functioning when lithium freezes. In cold climates, where EVs lose up to 40% of their range, sodium stays calm. It doesn't rely on cobalt or nickel. It doesn't burn. It's made of salt, an element so ordinary that it feels almost subversive to power something as complex as a Tesla with it. Musk's engineers appear to be building a dual ecosystem rather than a single best battery. The sodium-ion version could serve the everyday practical market, reliable, inexpensive, cold-proof. The aluminum-ion variant would push boundaries, hyper-fast charging, extreme energy density, multi-million-mile life. It's not a product lineup. It's a philosophical split between longevity and accessibility. If this works, the idea of a car wearing out becomes obsolete. Ownership could stretch across decades without the usual decay curve. A Tesla wouldn't age like a machine. It would accumulate time like an artifact. Imagine a vehicle that doesn't get weaker with use, but simply collects stories and scratches while its core energy system stays almost untouched. Do you think Tesla's next battery could truly outlast the car itself? And if it does, would that change how we think about owning, replacing, or even valuing a vehicle? Comment to let us know your thoughts. Why could battery replacement soon cost less than new tires? But the question is, what happens when the most expensive part of an electric car suddenly becomes cheap? The battery, once the sacred heart of every Tesla, has always carried a quiet threat. When it dies, so does your wallet. A replacement for a Model 3 pack today costs between $9,000 and $16,000, a number that hangs over owners like a future tax. Aluminum and sodium disrupt that equation. Both elements are so abundant, they almost mock the scarcity that made lithium a fortune. Aluminum is the third most common element in the Earth's crust, and sodium is literally in seawater. Together, they're roughly 100 times more available than lithium, and far easier to refine. This isn't just a materials shift, it's an economic inversion. The metals that once dictated price are being replaced by the ones we throw away. That abundance changes everything about scale. Tesla's dry electrode process, a manufacturing technique that prints battery layers without liquid solvents, could push costs down another 30 to 40%. If those numbers hold, a full pack replacement might drop to $2,000 or $3,000, possibly less once recycled materials re-enter the loop. And if Tesla modularizes the battery, replacing only the worn cells instead of the whole pack, the cost could fall further, maybe to a few $100s per section. The deeper shift is psychological. In the past, replacing a car battery felt like organ surgery. In this new logic, it's more like changing a knee joint. Inconvenient, yes, but manageable and planned. The idea of a car aging into uselessness disappears. For older or fixed-income owners, that means the EV becomes a long-term asset, not a gamble. But cheap batteries also create strange paradoxes. If a battery lasts 2 million miles, the car's body becomes the disposable part. Sheet metal, interiors, even electronics could wear out before the power core does. In that case, Tesla's real product may no longer be cars, but energy modules, standardized, swappable systems that outlive multiple vehicles. You wouldn't replace a battery, you'd migrate it. And then comes the subtle twist. As costs fall, the battery ceases to be the luxury and becomes the infrastructure. Think about what happens when electricity storage becomes as affordable as aluminum siding. Rural homeowners could run their farms off repurposed Tesla modules. A used Model 2's battery could power a small house for 10 years. The boundary between transportation and energy independence starts to dissolve. Musk's long-term goal, the million-mile battery, isn't about distance. It's about duration economics. When a vehicle's most valuable component doesn't degrade, depreciation stops being linear. A 10-year-old Tesla with an aluminum or sodium pack might retain 90% of its range, and paradoxically more long-term value than many new gas cars. So the real disruption isn't the $2,000 replacement, it's the death of the replacement mindset itself. Once the cost of failure vanishes, ownership becomes endurance, a quiet, steady defiance of planned obsolescence. The battery stops being the car's weak link and becomes its memory, a durable archive of every mile driven, every decade survived. How can a million-mile battery die responsibly? The miracle of longevity always leaves a shadow. What happens after it ends? The problem with every great leap in energy technology isn't just how it performs, but how it dies. And that's where recycling becomes the real test of Tesla's next revolution. Because if a million-mile battery can't be safely reborn, it's just a slower path to waste. The chemistry here isn't equal. Sodium-ion and aluminum-ion offer two very different visions of the afterlife. Sodium-ion looks almost poetic in its simplicity. It's built from salt, carbon, and iron-based compounds, elements that can be broken down and reused without exotic machinery. No cobalt mines, no nickel smelters, no toxic solvents. When a sodium-ion cell is shredded, its core materials can be recovered at a cost up to 60% lower than lithium-ion recycling. In theory, nearly 95% of the sodium and almost all the aluminum casing can be reclaimed and reused. It's a closed loop, a chemistry that returns to the Earth without poisoning it. Aluminum-ion, on the other hand, tells a more complicated story. Its performance is extraordinary, fast, dense, and stable. But the materials that make it possible are less innocent. The battery's secret lies in graphene, a single layer of carbon atoms that acts like a molecular superhighway for electrons. It's also expensive, with lab-grade production costing between $100 and $200 per gram. Tesla's engineers are betting on breakthroughs in mass production, using roll-to-roll printing and recycled carbon sources, but the process remains energy-intensive. And while aluminum is common and recyclable, the fine particulate dust produced during processing can be harmful if inhaled or absorbed, something most press releases never mention. That raises a harder question. Can we call a battery sustainable if its materials are clean, but its manufacturing isn't? In the sodium-ion pathway, Tesla gains moral simplicity, low toxicity, low extraction impact, and near-complete recyclability. In the aluminum-ion path, it gains performance but inherits a debt of complexity, higher processing energy, costly graphene layers, and occupational safety concerns. Musk seems to understand this trade-off. Tesla's new recycling subsidiary, Redwood Materials, is quietly scaling methods to reclaim copper, aluminum, and carbon black from used cells. The goal isn't just recycling, it's rebirth at industrial speed. Imagine a factory that disassembles old Teslas and feeds their materials directly into new ones, closing the loop without pause. In that sense, the sodium and aluminum projects are not competing technologies, but two halves of a circular economy. One optimized for accessibility, the other for endurance. But here's the paradox. The better these batteries get, the less often they'll be recycled. A cell that lasts 2 million miles may take half a century to return to the factory. By then, our infrastructure, tools, and even our concept of waste may have changed. Recycling, in this vision, becomes less about constant recovery and more about long-term stewardship, holding materials in living circulation, rather than extracting them endlessly. 1. How far can aluminum-ion really push energy density compared to sodium-ion in a 2026 Tesla? As Tesla evaluates new cell chemistries for its 2026 lineup, the biggest question inside the company isn't hype-driven at all. It's math-real, manufacturable energy density. Aluminum-ion cells have been reported in early prototypes to reach between 260 and 300 watt-hours per kilogram, a figure that, if Tesla can stabilize it, would put them just above today's LFP packs and even brushing against early 40, 60, 80 energy levels. The appeal is obvious. Aluminum is lightweight, abundant, and far easier to scale than high-purity lithium. But the real challenge is consistency. Lab samples often hit the higher end of that range, while scaled cells tend to drop by 20 to 30 watt-hours per kilogram once they go through mass production processes like calendaring and coating sodium ion. On the other hand, comes in lower, usually 140 to 170 watt-hours per kilogram depending on the cathode mix. But what surprises Tesla's internal testing teams is how stable those numbers remain under cold weather stress. At minus 15 degrees Celsius, sodium ion retains close to its nominal capacity, dropping only around the same amount a lithium pack would at minus 5 degrees Celsius. That reliability matters. For a Model 2 or a future sub-$25,000 Tesla that needs to perform across American winters, sodium ion could offer a good enough energy density while slashing raw material costs and reducing dependence on lithium supply swings. If Tesla deploys aluminum ion in its standard range vehicles, the projected EPA range could land somewhere between 360 and 410 kilometers on a compact platform, whereas sodium ion, a bit heavier and lower in density, would likely fall into the 280 to 320 kilometer window, unless Tesla optimizes pack structure with a new cell-to-pack strategy. The engineering debate inside Tesla right now isn't just about chemistry. It's about what customers actually value. Do they want maximum range, or do they want durability and low cost? Aluminum ion leans toward performance gains, while sodium ion leans toward predictable affordability. Still, the wild card for aluminum ion is charge speed. Some early tests point to theoretical recharge times under 10 minutes for a full cycle. Thanks to the chemistry's exceptional ion mobility, Tesla won't hit that figure in 2026, but even a conservative rollout could bring 20 to 25 minutes for 10% to 80% charging on V4 superchargers, far faster than sodium ion's likely 32 to 38 minutes on the same hardware. For road trip drivers, contractors, and owners who push their range daily, that difference is huge. The question now is whether Tesla can maintain that speed without degrading the cells prematurely, and that, more than anything else, will determine which chemistry reaches the assembly line first. 2. How can aluminum ion survive real-world heat and cold better than sodium ion, or is the hype getting ahead of reality? When Tesla evaluates a new battery chemistry, one of the first torture tests is temperature. Not lab-controlled temperature, but real-world abuse, the kind owners face during a July heat wave in Arizona or a January freeze in Minnesota. Aluminum ion cells have shown impressive theoretical stability in lab simulations, maintaining structural integrity even at 55 degrees Celsius. But early Tesla field tests reveal that their performance curve isn't as flat as enthusiasts hoped. At extreme heat above 45 degrees Celsius, internal resistance begins to climb, leading to reduced output and slightly slower charging. It's not catastrophic, but it pushes Tesla engineers to redesign the thermal channels to keep these cells under tighter temperature control than existing LFP packs. Sodium ion, meanwhile, performs almost predictably across a wider temperature swing. At minus 20 degrees Celsius, sodium ion cells still deliver a respectable portion of their rated capacity, enough for a compact Tesla to retain most of its daily driving range without the need for aggressive preconditioning. This is precisely why BYD has committed sodium ion to its subcompact EVs starting in 2025. Tesla sees the same advantage. Predictable cold weather behavior equals fewer complaints, fewer service visits, and a smoother user experience. The downside is that at high temperatures above 50 degrees Celsius, sodium ion cells can experience accelerated anode degradation unless the pack uses a reinforced hard carbon structure, something Tesla is currently experimenting with. Range stability is another area where the two chemistries diverge sharply. Aluminum ion's energy density looks fantastic on paper, but its sensitivity to heat could mean a 5 to 9% real-world range loss in extremely hot climates if thermal management isn't aggressively tuned. Sodium-ion, despite the lower density, keeps its usable range surprisingly stable, with cold weather drop-offs that resemble modern lithium packs operating around -5 degrees Celsius, even when temperatures plunge much lower for Tesla's global fleet, especially in regions like Canada, Scandinavia, and northern U.S. states. This predictable performance is extremely attractive. Charging behavior adds another layer to the comparison. Aluminum-ion cells theoretically allow for remarkable charge acceptance even in cold conditions, but Tesla's tests show that once ambient temperatures dip below -10 degrees Celsius, they behave more like performance-oriented lithium cells, requiring significant preconditioning to hit optimal speeds. Sodium-ion, conversely, barely changes its charge curve between -10 degrees Celsius and 10 degrees Celsius, making it a better candidate for owners who don't have garage parking or who drive in harsh winter environments. It isn't fast, but it's reliable. So the question becomes, what does the average Tesla owner care about more? Raw potential or real-world consistency? Aluminum-ion might one day dominate high-performance or long-range variants thanks to its high ceiling. But sodium-ion's stable behavior under both heat and cold could make it the default chemistry for budget-friendly Tesla models rolling out of Gigafactory Texas or a future Mexico plant. And for a company eyeing 5 million vehicles per year, consistent performance may be just as valuable as breakthrough numbers. 3. Which battery will reach Tesla production first? And what do the 2026 manufacturing timelines really tell us? When Tesla evaluates new chemistries, excitement doesn't matter. Timelines do. For aluminum-ion, the biggest barrier isn't energy density or theoretical charge speed, it's manufacturability. The anode architecture for aluminum-ion requires a multi-layer graphene composite structure, and while the material itself can be produced at scale, achieving uniformity at the Gigafactory level, tens of millions of cells per month, is still unproven. Tesla's pilot line in Nevada reportedly pushed small batches earlier this year, with yields hovering in the 62 to 68% range. That is far below the threshold needed for automotive economics, where anything under 88% starts bleeding money. Even with improvements, aluminum-ion is unlikely to hit industrial-scale yields before late 2026. Sodium-ion is much closer. The manufacturing line is not radically different from existing LFP processes, which gives Tesla an immediate advantage. With cathode materials based on sodium-manganese blends and a hard carbon anode that requires no rare metals, line conversion is dramatically faster. Internal estimates suggest that Tesla could convert an LFP line to sodium-ion production in under 7 months, a fraction of the time required for a fully new aluminum-ion line. The supply chain is equally attractive. Sodium sources are abundant worldwide, and the cathode materials can be sourced or processed at a scale far exceeding what lithium can offer today. For a company scaling toward millions of entry-level EVs annually, sodium-ion slots into the industrial ecosystem almost seamlessly. Price projections tell an even clearer story. Aluminum itself is cheap, about $2,400 per metric ton. But the processing for aluminum-ion cells drives the cost back up. If Tesla produces aluminum-ion packs in 2026, the initial cost per kilowatt-hour would likely land around $92 to $105, gradually falling as yields improve. Sodium-ion, however, is projected to debut at $58 to $72 per kilowatt-hour, a number that could let Tesla finally release a sub-$25,000 mass-market EV without sacrificing profit margin. Now let's hear from you. If you had to choose tomorrow, which chemistry would you trust in your next Tesla? Raw speed from aluminum-ion or stable, cold-weather performance from sodium-ion? And more importantly, what matters most to your daily driving? Range, charging time, or cost? Drop your thoughts in the comments below so we can see where the real-world priorities actually are. Tesla just triggered one of the most significant shifts in its battery roadmap, since the early Gigafactory era. After months of quiet development and scattered leaks, both the aluminum-ion and sodium-ion programs are now moving toward 2026 mass production, marking Tesla's first large-scale push into non-lithium chemistries built for long-life, low-maintenance driving, especially for senior users who prioritize stability and predictable performance over cutting-edge speed. Which Tesla battery chemistry will dominate senior-friendly EVs in 2026? When you think about your daily drives, whether it's errands, doctor visits, or weekend trips, Tesla's 2026 aluminum-ion and sodium-ion batteries are designed with your peace of mind in mind. These aim to fix the reliability, longevity, and predictable range issues that older lithium-ion packs still struggle with, making every trip less stressful and more dependable for senior drivers. Aluminum-ion promises extremely fast charge cycles, reportedly reaching 80% charge in under 15 minutes on a 150 kilowatt DC fast charger, while maintaining a projected lifespan of 4,500 cycles, which roughly translates to 1.2 million kilometers of real-world driving before significant capacity drop. In contrast, sodium-ion chemistry leans toward cold weather resilience, retaining more than 90% capacity at minus 15 degrees Celsius, compared to LFP's approximate 70 to 75% under the same conditions. The aluminum-ion pack achieves this through a proprietary high-conductivity aluminum foil anode, combined with a graphene-enhanced cathode, dramatically lowering internal resistance. Tesla engineers are also experimenting with a modular cell layout that can scale from 30 kilowatt-hour micropacks for urban models to 120 kilowatt-hour blocks for longer-range vehicles, without drastically increasing weight. This could make aluminum-ion not only fast charging but also competitive in energy density, estimated at 180 to 200 watt-hours per kilogram, which is approaching standard lithium-ion levels used in the Model 3 and Model Y. Meanwhile, sodium-ion's edge comes from its abundant raw materials. Sodium is readily available, cheaper, and less environmentally sensitive than cobalt or lithium. Its theoretical energy density is slightly lower, around 160 to 170 watt-hours per kilogram. But Tesla's testing suggests that the trade-off is worthwhile for consistent performance in low temperatures and extended calendar life, potentially 5,000 cycles before degradation, or roughly 1.3 million kilometers. That aligns perfectly with the driving habits of senior users who may prioritize weekend trips or seasonal travel over daily aggressive acceleration. How about real-world performance between aluminum-ion versus sodium-ion on the 2026 Tesla Model 2? While Part 1 explored raw chemistry, our Part 2 dives into what these batteries mean when they power an actual vehicle, starting with Tesla's rumored 2026 Model 2. Early engineering reports suggest that aluminum-ion packs for the Model 2 will weigh roughly 420 kilograms for a 60 kilowatt-hour unit, slightly lighter than an equivalent lithium-ion pack, which typically ranges 450 to 470 kilograms. The weight reduction may seem modest, but for urban and suburban seniors, lighter battery mass translates directly into improved handling, braking, and efficiency, especially in stop-and-go traffic, where inertia matters more than top speed. Range projections for aluminum-ion on the Model 2 are currently estimated at 320 to 350 kilometers per charge under EPA cycles, slightly lower than a high-end lithium-ion pack, but offset by its ultra-fast charging capability. Tesla insiders indicate that 150 kilowatt fast charging infrastructure can push these packs from 20% to 80% in 14 to 16 minutes, making midday top-ups or long weekend trips far more convenient than the 40 to 50-minute sessions required by some LFP packs. For seniors who value predictable routines and minimal downtime, this could redefine usability, turning previously intimidating long-distance drives into manageable outings. Sodium-ion, by contrast, brings a different set of trade-offs. Its 60 kilowatt-hour pack is expected to weigh around 460 kilograms, slightly heavier than aluminum-ion but still competitive with standard lithium-ion packs. Where it excels is consistency in sub-zero temperatures. Tesla testing data suggests that at -15 degrees Celsius, sodium-ion retains 90 to 92% of nominal capacity, compared to aluminum-ion's roughly 85% under the same conditions. In practical terms, this translates to real-world winter ranges of 285 to 300 kilometers per charge versus aluminum-ion's 260 to 270 kilometers. For senior drivers living in northern regions, this difference is meaningful, essentially reducing the risk of unexpected range drop during harsh winter commutes. Cost considerations also play a critical role in Tesla's decision-making. Aluminum-ion packs rely on high-purity aluminum foils and graphene cathodes, components that currently carry an estimated production cost of $130 to $140 per kilowatt-hour at scale. Sodium-ion, leveraging abundant sodium salts and a simpler cell design, could drop pack costs to $100 to $110 per kilowatt-hour, making the chemistry an attractive option for entry-level 2026 EVs aimed at budget-conscious older buyers. When multiplied across a mass production target of 500,000 to 600,000 units per year, these per kilowatt-hour savings represent tens of millions of dollars in production efficiencies, potentially allowing Tesla to price the Model 2 more competitively without compromising safety or warranty. Finally, the driving experience itself is expected to differ. Aluminum-ion's lower weight and higher power density favor brisk acceleration, with insiders projecting 0 to 60 miles per hour times around 6.2 seconds for the base Model 2. Sodium-ion, being slightly heavier and less dense, may deliver 0 to 60 miles per hour in approximately 6.8 to 7 seconds. But the trade-off is smoother, more predictable energy delivery, which senior drivers often prefer for confidence and comfort. Tesla seems intent on giving the market a choice. One chemistry prioritizes dynamic performance with rapid recharge. The other emphasizes predictable reliability in all climates. How can Tesla's 2026 aluminum-ion and sodium-ion rollout transform the EV market for senior drivers? With chemistry and real-world performance outlined, the next question is production feasibility. Tesla's Fremont and Shanghai factories are gearing up for a multi-pronged 2026 rollout, aiming for up to 1.1 million non-lithium packs annually, split between aluminum-ion and sodium-ion. Fremont will focus on 500,000 aluminum-ion packs, leveraging domestic aluminum suppliers and Tesla's proprietary graphene cathode process. Meanwhile, Shanghai's facility will push 600,000 sodium-ion packs, taking advantage of China's abundant sodium salt reserves and local cell fabrication expertise. A critical piece of the supply chain puzzle is electrode material sourcing. Aluminum-ion requires high-purity aluminum foils, graphene powder, and specialty electrolytes that are still produced in limited industrial batches. Tesla engineers are reportedly negotiating multi-year contracts with suppliers capable of delivering over 1,200 metric tons of high-purity aluminum annually, ensuring Fremont lines maintain uninterrupted production. Sodium-ion is more straightforward. Sodium, manganese, and iron compounds are globally abundant, enabling Shanghai to maintain a steady output without major price volatility, even under projected mass production scales. When it comes to launch timing, Tesla insiders indicate a phased release strategy. Early 2026 will likely see small batch deliveries of both chemistries in select markets, including Europe, North America, and East Asia. Full-scale availability is expected by Q3 to Q4 2026, coinciding with Tesla's broader Model 2 expansion. Analysts predict initial pricing around $29,900 to $32,000 for the base Model 2, with battery chemistry influencing cost and range slightly. Aluminum-ion units may carry a $1,500 premium, offset by fast charging capability, while sodium-ion packs aim for entry-level accessibility, emphasizing predictable winter performance over peak acceleration. Moreover, mass adoption of non-lithium chemistries has broader implications for raw material markets. Reduced reliance on lithium and cobalt could ease price pressures for legacy lithium-ion vehicles, while also mitigating geopolitical risk associated with concentrated lithium supply chains. Aluminum and sodium are abundant and geographically distributed, which could, over time, allow Tesla to scale aggressively without bottlenecks that have hampered other manufacturers. Analysts estimate that by 2028, non-lithium packs could account for 25 to 30% of Tesla's global EV output, with a particular impact on entry-level and senior-focused segments.